So,
This is fifth take.
this is not my fifth take, it's like my fourth. We had some issues. So, if you look at your periodic table, this is where everything is going to start for polar bonds. So, all these little numbers underneath are all standing for electronegativity. And the trend is as you go towards the right and as you go up, it's going to get higher. So fluorine has the highest electronegativity, and helium doesn't count because helium is a noble gas and doesn't want any more electrons. It's happy with what it has. So then, therefore, the next would be fluorine, and before neon as well. So for the same reason as helium as a noble gas. So basically, it doesn't matter too much, but it's basically just there's less electrons getting in the way, and there's more protons available to actually pull in the valence electrons. So that number basically just means it wants more electrons. It's going to hold them tighter, and in bonds, the electrons will actually shift a little bit closer to the more electronegative element, which is exactly what a polar bond is. So we have three main steps. The first one is going to be if it's a polar bond at all. So first we have a little just bond between oxygen and carbon. Obviously it's not real because we have like no valence being like fulfilled or like the octet, but it's okay. We're just going to look at just the bond itself right here. So we have oxygen and carbon. And if you look at the table or the periodic table, the electronegativity of oxygen is 3.5 and carbon is 2.5. If you subtract those two, it's going to be 1. And that's the entire premise of getting a polar bond, is you're just going to subtract the two of them and you want just the absolute value. So technically we should do delta En is equal to like 3.5 minus 2.5. But if you flipped it around, it shouldn't matter because that's what the absolute value is. So if you did 2.5 minus 3.5 in an absolute value, then you get absolute of -1, which is just 1. So it's just like the magnitude. But that doesn't really matter. You can just think about what the difference is between the two numbers, if that works better. So what we do is you're going to draw this arrow that we have here. So you draw it this way towards the part that's more negative with the arrow that way. And you want to draw the little positive at the end. So you kind of draw it across and a little hash. And that shows that this end is more positive. So the carbon in this sense is going to be more positive. And your teacher might do like a slightly positive like this, as it's shown in the green, and a slightly negative. You don't want to use an actual positive and negative because that assumes that it's the entire charge, which isn't true because these aren't ionic. It's just the electrons being pulled a little bit. Maybe if they were in the middle here, now they're a little bit closer to the oxygen. So they're still close to the carbon, just not that close, obviously. But they are a little bit closer to the oxygen this way. So we did talk about the electronegativity, but the biggest rule is that for the bond to actually be considered polar, it has to be greater than 0.4, like the difference between the two. So if it's not, then it's technically not a polar bond. But yeah, that's basically just like the magic number you want to focus on. There's no actual reason for it being 0.4. That's just when things start to act more like a covalent bond, or more like a polar bond instead of otherwise. But it's really just like a scale. So an example is if we just did carbon to carbon, both of these have 2.5 electronegativity, and when we subtract these out with absolute value, we'll get 0. And that would be a non-polar bond. So if you were asked if that's a polar molecule, you'd say no. So now we're going to go to symmetry. I'm going to rewrite this to make it more readable. But we're going to use the acronym SNAP. So SNAP, and that's symmetrical, is going to make it nonpolar. So these two are connected. and these two are connected. So non-polar and asymmetrical makes it polar. One thing to note is that when you go to number 2, I'm looking at symmetry, you're assuming that the electronegativity of the bonds is already greater than 0.4. Otherwise, you don't really have to go to this step. So if you had like a whole bunch of carbon-to-carbon bonds and you're trying to figure out if it's symmetrical, you don't really need to, because you already know that none of the bonds between any of the atoms are polar. So you don't have to worry about finding out if it's symmetrical or not as well. So if we take the carbon and oxygen bond that we were looking at up here and bring it down and look at its symmetry in an actual molecule as carbon dioxide, we see that we already got the electronegativity 1, and we can draw those little arrows as we already have here. You can see that they're kind of going in opposite directions, which is super important, but they're also equal. Both of them are a magnitude of 1, which is our number 3 that we'll get to in just a sec. But if you actually look at this now, you can see that one's going completely in one direction and one's going completely in the opposite. If you add these up or like kind of follow along, you're going all the way there and you're going to come all the way back. So you're starting and ending at the same place you started. So if you've done a lot of physics, it's just like adding vectors, which is super important. And that's kind of the basis of polar bonds here, as we'll get to in this next example. So looking at carbon tetrafluoride here, which just means there's a carbon with 4 fluorines in it. All of these bonds are going to be 1.5, and the more negative one is fluorine, obviously, because it has the highest electronegativity of 4, as you can see at all these. This is taking a tetrahedral shape, which just means that there's one going to be straight up and then one's going to be coming towards you. It's like a tripod if you think about it. And that's what this is. So these two are technically on the same plane on the page, and this one is going either into or out of the page, and this one's going the opposite. I forget which one's which, but the lines means it's going one way and the filling it in means it's going the other. But it doesn't matter too much. It's just showing that that is a tetrahedral shape. So if we go over here, we can look at this fluorine right here. We're going to take that one and make it this arrow. So it has a magnitude of 1.5. And if we take the carbon, the line here, we'll make that the 0 line. And then all the other ones, just by trigonometry, are going to equal a third of what their y value is. So the y value of this part, so this is the y and this is the x, and this is the entire one, which is 1.5. The y is going to be the 1.5 over 3. It's going to be negative because it's below that 0 line. And if you look over here, if we take that direction, there's going to be 3 that have this exact same configuration of the 1/3 y, which is why we're going to multiply it by 3. And that 3 is going to cancel with that 3, and we're just going to have negative 1.5. So when we add these two, if we like add the vectors, you know that it is symmetrical and they do cancel out. So even if each of the bonds are polar, because it's symmetrical, they're all going to just cancel out and equal nothing. So therefore that molecule would be non-polar. Now we're going to get to magnitude, which is really important as well, which we talked about a little bit. So now if you take that molecule we just had, I didn't draw it with the proper triangle or anything like that, but hopefully you get the shape. It's going to be the same tetrahedral, but now we have 3 hydrogens at the bottom instead of fluorine. So let's fill this out. So the fluorine is going to be the more negative, so the positive is at the carbon end. That's going to be 1.5. The hydrogens are going to be actually the positive part here, because theirs is 2.1, while the carbon is 2.5. So the hydrogens are going to have the positive hash there. And each of these are going to be 0.4. So just barely polar, but polar nonetheless. And then we can now take this and do the exact same thing we did up here. So before it was this fluorine, and obviously we're just going to take the one fluorine here because it's nice and simple and it's already straight up and down. So we're going to say that fluorine there, which is going to be the same as this arrow, is equal to 1.5. We can say positive if you want. And we have 3 other arrows we're going to get the y components of. And those y components is going to equal, just by trigonometry, a third of what their value is. So the y value is 0.4, but we're going to make it negative because it's below. It's going the opposite direction as what we've set to positive up here. We're going to divide it by 3, but there's also 3 of them. So those 3's are going to cancel out, and we're just going to get the negative 0.4. So now, if we get the sum of the y components here, we're going to have the positive 1.5, and we're going to have the negative 0.4, and therefore the whole bond is going to be positive 1.1. And remember, our positive direction was up, like this. So therefore, because we're talking about electronegative here, the electronegative part is going to be up, where we've set positive. And therefore, the positive part is down here. And the whole thing is going to be 1.1. So that means in this molecule, the electrons are all going to be shifted up towards the fluorine just a little bit more than everything else down here, which is super important for intermolecular forces, as you'll hopefully learn either already or soon. So if you didn't get anything, just let me know, but that should be enough to hopefully learn a bit about polar bonds.